Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the modeling of non-isothermal CSTR. So if we'll see, this is the non-isothermal CSTR here. So in this case, this is the CSTR here. The feed is being charged considering F0, Ca0, T0 temperature inside the reactor having volume V, temperature T, and inside concentration Ca. So this temperature is not constant, actually it can change. To control the temperature, somehow we are feeding a cooling water as flow rate Fj and the temperature Tj, and volume of jacket is Vj, and temperature inside the jacket is Tj. So the metal ball thickness is very thin actually, so in that case that there is no temperature, the distribution within the metal ball, so metal ball temperature inside the reactor can be assumed same. So reactor outlet goes with a flow rate F, concentration Ca at temperature T. So we have to find all governing equations for this case. So here the reaction is considered as a reversible reactions. A goes to B with a K kinetic constant. This is nth order reaction with respect to A. Lambda is heat of the reactions. To remove this heat of reactions, you have cooling jackets. Around this, cooling water is added inside the jacket as volumetric flow rate Fj with the inlet temperature Tj0. The volume of water jacket is Vj, you already know that. So the metal ball is assumed to be negligible mass, and in order to avoid the thermal inertia. So if you see the overall heat transfer, that Q equal to U A T minus Tj. U is overall heat transfer coefficient, Ah is heat transfer area, T is reaction temperature, Tj is jacket temperature. So this is overall heat transfer. Now if you see the total mass balance inside the reactor, so this is the accumulations of mass within the reactor, rho into V upon dt. Mass coming in rho F0 minus rho F, considering the constant density system here, and with very liquid hold up. So dB upon dt equal to F0 minus F. Now the component balance dBCA upon dt equal to F0 Ca0 minus FCA minus KV Ca to the power n. Now if we do the energy balance, so energy accumulated within the tank, within the reactor actually, so enthalpy coming in with the feed, going out with the product, enthalpy generated with the reaction, and this is the energy removed as a cooling coil. So by taking the density out from here, so if you say here that B into H upon dt equal to rho F H0 minus H lambda Bk Ca to the power n UH T minus Tj. Now H can be substituted as Cp into T. So if you just substitute Cp into T, d dBT upon dt, rho Fcp T0 minus T lambda Bk Ca to the power n minus UAT minus Tj. For jacket energy balance, the enthalpy balance within the jacket, so enthalpy within the jacket equal to the enthalpy coming in with the cooling water, enthalpy going out with the cooling water. This is the energy supplied from the reactor to the jacket. So here that H can be substituted now C into T actually. So this you have rho Vc dt upon dt equal to fj rho j cj tj naught minus tj plus uah t minus tj. So where this rho j is density of cooling water, h is enthalpy of process liquids, hj enthalpy of cooling water. Now this hydraulic of reactors, the flow control outside the reactor need to be controlled. So you need a label control to control the flow rates. So F can be calculated Kb, V minus Vm. H is Cp dt, Hj is Cj dt. So Arrhenius equation is given by K equal to K0 exponential minus E upon RT. So equation 2 to 6 are our required model equations, and the 5 unknowns B, F, C, A, T and Tj, and for that we have need initial conditions T0, F0, Ca0, Fj. So we have considered there the heat transfer area. So inside the reactor the volume can change depending on the flow rates. So we need the active area for the heat transfer. So we can calculate from this equation, considering that a flat bottom cylindrical the reactor with diameter d and no jacket is being applied on the bottom side. So the jacket is only applied on a cylindrical portions of the reactor. So in that case the volume inside the reactor, entire volume will need to be covered. So it's pi d square by 4 into h. So in that case we can derive the formula of area for heat transfer is 4V over d. So assume that overall heat transfer coefficient U is constant, so it may be a function of coolant flow rate Fj. So these are the model equations and can be solved by these forcing functions, the initial value T0, F, Ca and Fj. Thank you.